Hello everyone, welcome to the 10th lecture of the series on AI using Python. In this lecture, we will be discussing about multivariate regression. As the name implies, in multivariate regression, the input and output data are multivariate. This means the input data and output data contains observations of more than one variables. Let small letter n denotes the number of input variables and small letter m denotes the number of output variables. Then in multivariate regression, we have n and m will be greater than 1. Now in multivariate regression, our objective is to find a model or a function that fits the input-output data. Here, the function can be either linear or nonlinear. Based on this, we can have either multivariate linear regression or multivariate nonlinear regression. We will start with multivariate linear regression, in which the model is a linear function as given in this equation, where x is the input, which is an n-dimensional vector, y hat is the predicted output, which is an m-dimensional vector, and A is the weight matrix, which is an m by n matrix, and B is the bias term, which is an m-dimensional vector. Now, in multivariate linear regression, the value of n and m will be greater than 1, and our objective is to find an optimal weight A and bias B for a given data. And for that, we will be using the available data or the training data, which consists of n observations of the inputs, which are denoted by x1, x2 up to xn, and n observations of the output, which we denote by y1, y2 up to yn. So here this capital N denotes the number of observations of input and output, whereas small letter n denotes the number of variables in each input observation, and small letter m denotes the number of variables in each output observation. If m is equal to 1 and n is greater than 1 in the case of linear regression, we call it as multiple linear regression. Therefore, in the case of multiple linear regression, the output will be univariate. Next, we move on to the illustration of multivariate linear regression, and we start with the multiple linear regression, in which we consider the input data with the two variables. Now we can import the libraries, and in this illustration we will be using the NumPy, Matplotlib, and sklearn libraries. We will be generating the data from the linear equation of the form ax plus b, where a and b are defined as here. Now let's define x as a 2D array in which the first row contains 1000 equally spaced data points between 0 and 10, and the second row also contains 1000 equally spaced data points between 0 and 10. Here, this term denotes the first row of the array x, which is corresponding to the variable x1, and this row corresponding to the second row of the array x, which is corresponding to the observations of the variable x2. Now we can plot x1 versus x2 versus y in the 3D space, which gives the plot as shown in this figure. Here we can see that the graph is a one-dimensional curve. This is because of the reason that the input points that we have chosen are from a line which satisfies x1 equal to x2. And this line will be in this x1 x2 plane for this horizontal plane, and for all the points from this line we computed the values of y using the linear relationship, and the y coordinate is taken along this z axis. So that's why we got a line that looks like this. Now to get a 2D curve, we have to take the x1 x2 points from a surface in this horizontal plane, and a simple way to do that is to use the meshed grid function, where the meshed grid function will take each possible combinations of x1 and x2, which generates large number of points from the x1 x2 plane. So here we define x as a 2D array, which is same as before, and from this the x1 and x2 are constructed using the meshed grid function, which takes the first row of x and the second row of x as its input. Here this x1 is a 2D array where each row contains a copy of the first row of x, and x2 will be a 2D array where each column will be a copy of the second row of x. Now we can define y using the linear relationship, and here this y we consider as the actual output, and this a and b are considered as the actual model. Now to generate the training data, we will be using the random state function, and xtr is defined as a 2D array which contains these elements, and ytr is defined as a into xtr plus b plus r, where r is a random array. Now we can put xtr1 versus xtr2 versus ytr, and x1 versus x2 versus y, which gives the plot as shown in this figure. Here, this red dot is corresponding to the training data and this black surface is corresponding to the actual data. So here we can see that the training data is chosen in such a way that the data is more spread across this surface. And another way to generate the training data which is more spread across the surface is to use the random function. And let's say if you are using this function for generating the training input, then it will contain 100 2D points which are spread across the x1 x2 plane, for which we can compute the training output using this equation. And we can plot xtr versus ytr and x versus y as before, which gives the plot as shown in this figure, where we can see we have more data points now. And here this last line can be used for rotating the axis, using which we can rotate this plot. For example, if we are not using this, it will be giving some default angles. And the plot will be as shown in this figure. We can use the linear regression function from the sklearn library to fit a linear model to this training data. And we denote the model as f underscore L. Now using this xtr and ytr, we can train the model. And for that, we will be using the fit function. And f underscore L dot coefficient will give us the weight matrix, which is denoted by a underscore L. And f underscore L dot intercept will give us the bias term, which is denoted by b underscore L. And using this weight and bias, we can predict the output for the input data as in this equation. And we denote the predicted output as y hat L. Now we can plot xtr versus ytr, x versus y, and x versus y hat, which will give us the plot as shown in this figure. Here, this red dots corresponding to the training data, and this black surface is corresponding to the actual output data, and this green surface is corresponding to the predicted output data. Here we can see that the predicted output is closely matches with the actual output. Now we can move on to the illustration of multivariate linear regression, in which the data is generated from a linear equation of the form ax plus b, where a and b are chosen as in this equation. And here we are considering the data will contain 3 inputs and 2 outputs. So therefore, A will be a 2 by 3 matrix and B will be a 2 by 1 vector. Now XTR is generated using this random function, and XTR will contain 100 observations of a 3-dimensional vector. And then YTR is computed using the equation AX plus B plus R, where R is a random array. Now we use the linear regression function to fit a linear model to this training data. And as before, we denote the model by f underscore L. Now using the training data, we can train the model, and using which we can predict the output for the input data. And in the trained model, we denote the weight by a underscore L and the bias by b underscore L. And we have a underscore L will be as shown here, where we can see that the elements are closely matches with the actual values. And similarly, we can print the elements from the bias vector, and here we can see that the elements are approximately matches with the actual values. Now we can use the mean square error function from the sklearn library to compute the mean square error with the linear regression model. And here we will be finding the error between the training output and the predicted output. And we denote the error as MSC underscore L. And we can see that the error is small. Next, we move on to the multivariate nonlinear regression, in which the model is nonlinear and can be represented as in this equation, where x is the input, y hat is the predicted output, and f is a nonlinear mapping. N is the number of input variables and m is the number of output variables. And in the case of multivariate regression, both n and m will be greater than 1. Now, as a special case, we can have multiple nonlinear regression, in which the number of output will be equal to 1. We can use different functions for fitting the input-output data, and the neural network, which we have discussed in the previous lectures, can be a suitable choice in most of the cases. And in neural network, the model will be of the form as in this equation, where we denote the function as fnn, which is the composite function of this form, where f0, f1 up to fl plus 1 are the layers of the neural network. Then the weights and biases for each layer in the neural network will be the elements of the parameter vector p, and our objective is to optimize these parameters. To find P, various optimization algorithms can be used, which computes the optimal parameters by minimizing the loss function or the cost function, which is basically a function of the training error. Next, let's move on to the illustration of multivariate nonlinear regression, and we start with the multiple nonlinear regression, in which we consider a data set with two inputs. And as before, we will be using the mesh grid function for creating more number of points from the x1 x2 plane. And here the output y is generated using a1 into x1 square plus a2 into x2 square plus b, where a1 is chosen as 3, a2 is chosen as 2, and b is also equal to 2. Now the training input xtr is defined as 100 2D points from the x1 x2 plane, and the training output ytr is defined as a1 into xtr1 square plus a2 into xtr2 square plus b plus r, where r is a random array. Now we can plot xtr1 versus xtr2 versus ytr and x1 versus x2 versus y in a 3D space, which gives the plot as shown in this figure, where we denote the training data by these red dots and the actual data by this black surface. Now using the MLP regressor function from the sklearn library, we can fit a neural network to this training data. And here we can define the structure of the neural network, where we will be using 3 hidden layers, with each layer contains 3 neurons. And the activation functions for each hidden layer is chosen as tanh, and the solver for the optimization is chosen as LBFGS, and the maximum number of iterations is set as 10,000. And we name this neural network as f underscore nn. Now we can train the neural network using the training data xtr and ytr. And using the trained neural network, we can predict the output, and the predicted output we denote as y hat nn. Now we can plot xtr versus ytr, x versus y, and x versus y hat nn in a 3D space, which gives the plot as shown in this figure. The training data is denoted by these red dots, and the actual data is denoted by this black surface, and the predicted output data is denoted by green dots. Here we can see that the green dots are closely matching with the red dots, which means the predicted output is closely matching with the training output. Next, we can move on to the illustration of multivariate nonlinear regression. And for generating the data, we will be using the nonlinear equation ax square plus b, where a and b are chosen as here. And xtr contains 100 observations of the 3D vector. And ytr is defined as a into xtr square plus b plus r. Now we can normalize the input and output data using the standard scalar function from the sklearn library. And this normalization will result in faster convergence of the optimization algorithm, and also it can result in more accurate model. And using the normalized xtr and ytr, we can train the neural network. And using the trained model, we can predict the outputs. Now we can find the weights in the trained model using the model.coefficient command, which will give the weights as shown here. And similarly, the bias terms is given by the model name.intercept command, which will give the bias terms as shown here. This will give the weights for layer 1, layer 2, layer 3, and the output layer, and similarly the biases as well. Here also we can find the mean square error, and here we will be finding the error between the training output ytr and the predicted output y hat nn. And we can see that the error is very small in this case. This means the neural network can approximate this multivariate input-output data with sufficient accuracy. With this, we come to the end of the discussions on regression. And in the next lecture onwards, we will be focusing on classification and its various algorithms. That leads us to the end of this lecture, and thank you.